Hi, and welcome to the part 4 of this video series. On this video, we'll be taking a look at how we can calculate the roots of any given equation using two different methods, the secant method and the Newton's method. So let's take a look at how we can do that in Python. First of all, let's say we have a function that kind of looks like this. So firstly, what the secant method tells us is that what we want to do is, first of all, we want to assume any random values, x0 and x1, which hopefully is between, the root lies between these two values. And once we have that, what we do is we calculate the function at x0 and the function at x1. Once we have these values, what the secant method tells us is that in order to calculate x2, we can do x1 minus the function at x1 multiplied by x1 minus x0, and this whole thing is divided by the function of x1 minus the function of x2. Once we calculate, this is actually x2. Yeah, so once we calculate x2, what we do is we calculate a function of x2, and this value has to be equal to 0 in order for the value x2 to be the root of this equation. Now, clearly we can see that the first thing that's important to, so what happens here is that on the first calculation, we might not end up with a value of x2 that actually gives us the function to be 0. So what this means is that we need to do these calculations iteratively. So what this means is that if the function of x is not equal to 0, what we do is we say that our new x0 is actually equal to our old x1, and our new x1 is equal to x2, which we just calculated. And using these two, we simply go back to step 1, where we calculate x0 and a function of x1, and then we again calculate x2, and then we again calculate function of x2 at that, and we check if that is equal to 0. If it's not, we keep iteratively doing these calculations again and again until we end up with a value that is where function of x2 is actually equal to 0. So let's see how we can do that in Python. So first of all, I've imported a bunch of things here, mainly JAX NumPy, and I edited the configuration of JAX so we can actually use 64-bit numbers instead of 32. So the first step would obviously be to actually create a function that we can find the roots of. So let's define a function f which takes x as inputs, and it returns a function that is let's say the function has 3 roots. One at say 0.3, another root at say 0.1, and another root at, let's say the root is at negative 0.3, positive 0.1. I'm making mistakes here. It's negative 0.3, positive 0.1, and positive 0.5, let's say. X minus 0.5. We'll do that, and then let's plot this graph out to see what it looks like. So fig equals make underscore subplots, and then fig.add underscore scatter. Let's make a two-dimensional scatter diagram where x is equal to x, and let's say y is equal to our function, and let's say our so our mode will be lines. So we don't get a bunch of dots, but instead we get like a line diagram. What I'll also do is update the layout so it looks nice, where I'll set the width to 600, the height to 600, and I'll also use a template called plotly underscore dark. Obviously, we also need to give this our x value a bunch of values. So what we'll do is say x is equal to np dot linspace. Let's go from negative, where does it go? It's a -1. So let's go from negative 0.5 all the way to 1. And let's have 100 values in between. So let's see what that looks like. Oh, looks like there's an error here. Oh, it should be function of x here. All right, there we go. So this is the graph that we have. We can see that there are roots at roughly around 0.3, and then 0.1, and then 0.5. So yeah, we need to actually calculate these roots now. So for the secant method, what we need to do is let's define the method as a function. So like define secant, and we'll give this our function f to start with. There's also going to be a bunch of other inputs, but we'll put that in as we create this function. So first thing that we need to do, we first need to calculate function 0. Actually, we already know that we're going to make two guesses, x0 and x1. So let's put that in as inputs right away. So x0 and x1. Now, once we have our guesses, we calculate our values of the function. So f0 is simply function of x evaluated at x0. Likewise, function f1 will be the function of f evaluated at x1. Oh, looks like I made some mistakes there. There we go. Once we have that, we're going to start our iteration now. So that would be a for loop for I in range. So we want to determine just how many times we want to do these iterations. We could do a while loop here, but the disadvantage of that is that if we make any mistakes here and our function doesn't actually converge, it will just do these calculations indefinitely. So we definitely want to make limitations on that. So let's say we only want to do these iterations n number of times until our function gives an error. So I will set n at, say, 50. So we don't want to calculate this secant method any more than 50 times. So we have that. And under our iterations, what we want to do is we want to calculate x2, as we saw in our formula previously. And this is equal to x1 minus our function f1 multiplied by, let's put this whole thing in a bracket actually. Yeah, so we multiplied the function of 1 by the difference between x1 and x0. And we divide this whole thing by the difference between function f1 and f0. And once we have that, we calculate f2, which is simply our function f evaluated at x2. Now, once we do this, what we want to say is if the absolute value of our function f2. Oh, actually, instead of doing that, first let's do this. If the value of f2 is equal to 0, we want to break out of the loop. But the problem is, in order to reach exactly 0, we might just have to do a few too many calculations, like hundreds of calculations. So instead, we will save some computing resources by saying that we only want to reach a number that's close to 0. So say 1 times 10 to the negative 10. So what I'll do is make this a tolerance instead of an actual value. So I'll put that in as an input right here. Our tolerance would be 1e to the negative 10, which is pretty close to 0. So we have that, and our conditional statement changes to if f2 is less than our tolerance. Now the problem with doing this is that if we reach a negative 1000, it'll also assume that we've reached our root, which is simply not true. So what we'll do is make this an absolute value. So any value calculated in f2 we look at its absolute value and we want it to be very close to 0 up to the magnitude of -10. So yeah, we have that. If the condition is met, this breaks out of the loop. If it's not met, we want to update a few values and then go back to step 1 and do this again. I've already mentioned this, so what we want to do now is set our x0 to our old x1, and then we want our new x1 to be set to our calculated value of x2. Likewise, we're again going to create our function f0, which will be function f evaluated at x0, which is again our old x1. And finally, we want to calculate f1, which is equal to our function of f evaluated at x1. Again, x1 is our newly calculated x2, as we can see right here. So yeah, that's pretty much all we need to do. Once we're done with that, we're simply going to return our value of x2, so we know where our root lies. And just for fun, I'd also like to see just how many iterations we actually need to do. So let's run this, no errors. Now let's try to find out one of the roots of this equation. So I'm going to base secant, and we're going to give this our function f, which is actually f. And then our initial guess should be, say, -2. Our final guess, let's say, is 0.3. And we already have our number of iterations and tolerance decided right there. So I'm going to run this. And we got an error, the truth value of an array. It looks like I forgot to add 1 here, so it's just an x. So now everything should be fixed, hopefully. And there we go. Okay, so it says -0.3, which is in fact one of our roots, as we can see right here. Yeah, right here. So yeah, that's how we find the root of a function using the secant method. Now let's take a look at how we can do this using the Newton's method. So like we did last time, say we have another function right here. We have this function. Now, according to Newton's method, we only need to make one random guess for the value of x. So let's say what we do here is we assume a value of x0, and then using that value, we calculate the function, we evaluate the function of the curve at x0. And once we have that, what we do is we take this function and we calculate its gradient at x0. Now, what Newton's method tells us is that x1 should be equal to x0 times the function of x0 divided by the gradient of the function of x0. Now, this actually gives us the value right here at the axis, and what we want to know is that our our value of the function of x1 needs to be equal to 0. Now, if this isn't the case, if the function isn't equal to 0, what we do is, like in the secant method, we say that our new value of x0 is actually our old value of x1 that we calculate right here. And once we have that, we go back to step 1, calculate the function, the gradient, and this again, and we finally calculate our value of x1. We evaluate the function at x1, and if this is equal to 0, then that will be our root. So let's take a look at how we'll do that in Python. So first of all, we already have our function defined. So let's define a new function to do the Newton's method. So define Newton. Again, it's probably going to be the same things that we're going to use as inputs for this function. So like we need our actual function of the curve, and then we need an initial guess. We only have one guess here, so we don't need x1. And we also need the number of iterations we want to do, which I'll set at 50. And finally, we also need our tolerance, which I will again set at 1e to the -10. Okay, so first things first, what we want to do is calculate the value of function at x equals 0, which is this. Once we have that, again, we're going to start a for loop for I in range of n. What we want to do is now we want to do the calculation. So x1 is equal to x0 minus our function of f at x0, and we divide it by the gradient. So let's actually calculate the gradient right here outside of the loop. What we can do here is we can use the gradient function in JAX. So the way to do that would be I'd store this gradient in the variable m, and this would be equal to jax.grad, and we'll provide the function f, and then we will also provide the allow underscore integer as true. There's that. And then what we want to do inside this for loop while calculating the value of x1 is we want to evaluate the gradient at x equals x0. So that way we can calculate x1. Now we calculate f1 by evaluating the curve at x1. And what we want to do now is check if f1 is equal to 0 or is close to 0. So that would be if the absolute value of f1 is less than our tolerance, then we want to break out of the loop. If that is not the case, what we want to do is we set our new x0 as our calculated value x1, and we again evaluate f0 at x0. So that would be, we can evaluate the curve function at x0. So there's that, and we finally return the value of x1, and I also want to know how many iterations I have to do, so I'll put in I in there as well. So there we go, no errors. Now let's do the same thing. Newton, and we provided the function f. Our initial guess would be 0.3 like we did last time. And once we have that, I don't think there's anything else we need to supply to this function. So let's try running it. And we get the value of negative 0.3, just like we did right here. So yeah, so one interesting thing that happened here is that we had to go through 9 iterations on the secant method, whereas we actually just got a 0 here, which is interesting. So this probably means that we got our iteration on the very first try here. So yeah, so Newton method looks like it is kind of more efficient than secant method.